Upon completion of this chapter, you should be able to identify and discuss the advantages and disadvantages of coiled tubing operations, identify various coiled tubing operations and purposes including completing a new reservoir, stimulation and fracturing, reworking an existing reservoir, fishing, cementing, well kill, logging or perforating operations, and perform calculations to provide a water cushion against formation pressure when perforating. Coiled tubing units are often used to clean up producing wells. The removal of fill material, such as formation sands or other particulates, is often performed with coiled tubing while the well is still producing.
Circulating friction pressure loss represents the amount of pressure required to circulate the fluid through the coiled tubing system. This is the pressure read at the pump discharge while circulating and represents the pressure required to overcome the friction losses within the circulation loop.
Total circulating friction pressure loss can be broken into 6 components: the surface piping from the pump to the reel, the spooled tubing on the reel, down the coiled tubing, through the bottom hole assembly, the return flow annulus, and the return flow surface piping to the choke. For well control purposes, the friction pressure loss in the annulus is often negligible when compared with that inside the coiled tubing. An exception is for the case of coiled tubing with a diameter similar to the internal diameter of the well, where the annular gap is small.
Capacity is a term used to describe the volume per unit length enclosed within a tubular or annular space of a wellbore. The determination of the capacity in barrels per foot of a tubular is capacity is equal to the internal diameter squared divided by 1029.4, where 1029.4 is a constant and internal diameter is the inside diameter of the tubing in inches.
This definition can apply to either the coiled tubing or the host production string, into which the coiled tubing will be inserted.
Volume is defined as the measured space occupied by an object. Measured space means that volumes are three-dimensional and generally measured in terms of length, width, and height. Common units of measure for volume in well control operations are cubic feet, cubic inches, barrels, and gallons. Take some time to familiarize yourself with the conversion factors in the table as they will come in handy throughout the course. Boyle's law can be used to illustrate some important points about the behavior of a gas influx as it is circulated or allowed to migrate up the well.
Assume a single barrel of gas is swabbed into the well as tubing was pulled from the well. There is no attempt at controlling the gas expansion in the well. It is unlikely that the barrel of gas will remain a single, discrete bubble, as some of the gas may be dissolved into the liquid, and some may percolate upwards, with the remainder stringing out in length as it begins to migrate. However, in this example, imagine that the gas influx remains as a single bubble, and the well has a constant internal diameter from top to bottom. State 1. On bottom, the gas is initially contained by the hydrostatic pressure of the fluid in the well, which is equal to 5,200 psi. The density of the gas is much less than the density of the wellbore fluid, which is a 10 ppg liquid. Wellbore fluids will tend to segregate due to gravity, with lighter gas migrating toward the surface. State 2. When the gas bubble reaches 7,500 feet, the hydrostatic pressure above is 3,900 psi. Using Boyle's law, the volume of the bubble is calculated to be 1.33 barrels. The pressure inside the bubble is now equal to the hydrostatic pressure above it, or 3,900 psi. The gas bubble is slightly longer in length, and as a result, 0.33 barrels of working fluid has been displaced from the well. This decrease in fluid reduces the total bottom hole pressure to 5,197 psi at the bottom of the well. The pressure at the surface remains 0 psi because the well is not shut in. State 3. When the bubble reaches 5,000 feet, the hydrostatic pressure immediately above the bubble will be 2600 psi. The bubble is now halfway up the wellbore, and again, using Boyle's law, the volume of the bubble is calculated to be 2 barrels. There has been a 2-barrel gain in the pits. State 4. At 2,500 feet, the hydrostatic pressure immediately above the bubble is now 1,300 psig. The gas volume is now 4 barrels. Hydrostatic pressure at the bottom of the well is now 5,160, and the surface pressure remains at 0 psi. State 5. At 1,250 feet, the hydrostatic pressure immediately above the bubble will be reduced to 650 psi. The gas volume is now 8 barrels. State 6. At the point where atmospheric pressure is reached, the pressure is 14.7 psi, and the single barrel of gas, which was swabbed in at 10,000 feet, will have increased to about 350 barrels.
If the well were left open, at some point in the gas migration, the bottom hole pressure would be reduced below the actual formation pressure. An additional influx would have entered at an ever-increasing rate. The working fluid in the well would be unloaded by the imbalance, and the well would ultimately blow out.
The flash point of a liquid hydrocarbon is the lowest temperature, which gives off enough vapor at atmospheric pressure to create an explosive mixture. The effects of gas solubility differ from the flash point of a liquid hydrocarbon. It is possible that many liquid hydrocarbons flash immediately after exiting a choke line, where the pressure is rapidly reduced to the atmospheric pressure and the ambient temperature is greater than the flash point temperature. This is a major reason why the exit to the vent lines coming from a choke manifold or liquid gas separator are located far from the CT unit or up a derrick if offshore.